this video, we are going to have a look at some Boolean expressions and its realization using gates such as AND gates, OR gates, the inverter gate, as well as we would try to motivate the construction of the given Boolean expression using universal gates such as the NAND gate. Okay, so let's, for instance, have a look at this Boolean expression. Now, how do we realize this Boolean expression? So we can just develop the NAND gates for the inputs, because we have x1 ANDed with x2 as well as x3 and x4, and then the outputs of this could be fed to an OR gate. Okay, so this would be x1 and x2, and this would be x3 and x4, and then we can clearly see that the output here is nothing but x1 and x2 ORed with x3 and x4. So now the next question would be, could we realize this Boolean expression using NAND gates alone? Okay, now how do I go about doing that? Now we could see that if we inverted the output of each of these NAND gates and we inverted the input, we inverted these two inputs to these OR gates, to this OR gate, okay, then the behavior of this circuit should not change, okay, which is clear, because if we negated the output of this and then we negated the input of this, so the two negations would cancel each other and the circuit would be the same as that of before. Now we will quickly write down that as below. So let's have x1, x2 getting into the AND gates as before. However, instead of the AND, we use a NAND. Okay, that is the AND followed by an inverter. Okay, now which gets into an OR gate. Okay, but with inverters to the inputs of the OR gate. Okay, now we can now clearly see as to what the various expressions should be. Yeah, so we can clearly see that the new circuit below here is the same as that of the circuit above. Okay, in terms of the functionality, yeah, but we have changed these AND gates, these two AND gates, to these two NAND gates, and we have also changed the inputs to this OR gate with an inverter. That is where we have placed an inverter as we have just seen. Now the thing is, so now this expression could be written down as what? So we can see that this can be written down as this. So all that I've just done is I've used the De Morgan's law, to just write down this expression in this form. Okay. Now, which implies that this OR gate with its inverted inputs could simply be changed to a NAND gate. Okay. All right. So we could just see that the OR gate that we had previously with inverted inputs could simply be replaced with that of NAND gate. So, which in other words means to say that we have realized the given Boolean expression using NAND gates alone. Now, we could see that this schema could be generalized to any Boolean expression, okay, of this form, or even more complex Boolean expressions could be realized using NAND gates only. Okay, but you know, I'm just showing a scheme here which can be easily generalized to any other Boolean expression of this form. Yeah. So we will have a look at another example. To just see as to how we can just make use of this schema that I have shown you. Okay. Now let's have x and y as inputs. So obviously we have 4 rows here. Okay, and let the output be 1, 1, 1, and a 0. So let's just assume that that we have been asked to construct a circuit which, given as inputs x and y, ought to realize this output. Okay. Now, what do I do if I need to realize this table using a circuit consisting of and OR gates? So I just choose those rows in which I have the output to be equal to 2. So here in this table we have 3 such rows. Okay, so which is the same as x and y. Okay, and x and not of y. Alright, so all of these expressions realize the 1 here, and I also have not x and y, and clearly we are looking to OR all of these expressions because any one of them could be equal to 1. So we need to realize this given expression. Alright. Now, how do I go about doing that? So we can just use the schema that we have seen before. Alright. So I can feed in as input x and y. Okay. And the other gate has inputs x and not y, and the third AND gate has as inputs not x and y, and these could all be OR. Okay. Now in theory we can have an OR gate with 3 inputs. Okay, in theory, and of course it's I mean we can clearly see that an OR gate with 3 inputs can be realized using an OR gate with 2, using a few OR gates with 2 inputs. Okay, so it's an easy exercise because the OR operation is associated. So we should be able to realize an OR gate with 3 inputs using a few OR gates with 2 inputs. And similarly, we should be able to realize an AND gate with 3 inputs using a couple of AND gates with 2 inputs. Okay. So anyway, so this is the circuit to realize the given expression. Now, if I was asked to realize this given expression using NAND gates alone, what I do is I just follow the same schema that we followed previously. That is, I replace the AND gates with NAND gates. Okay, that is, I put an inverter to the output of each of the AND gates, as well as I could put an inverter just before the input to my OR gate, which again, as we have seen before, we could rewrite this the OR gate, okay, of course with its inverted inputs using an NAND gate. And we could just clearly see that this is because of the De Morgan's theorem that we have seen before. Okay, you guys can easily convince yourself that this is indeed the case. All right. Now, I did talk about the associativity of the OR operation and the associativity of the AND operation. The associative property of the AND and the OR operations facilitate a 3-input AND gate to be realized using 2 AND gates with 2 inputs each. All right. And similarly, 3-input OR gate can be realized using 2 OR gates of 2 inputs each. However, the question to ponder about is the NAND operation associative? If it is associative, then we could realize a 3-input NAND gate using 2 NAND gates of 2 inputs each, okay, but which is not the case, unfortunately. Okay, the NAND operation is not associative, so we need to introduce a bit of an artifice when we want to realize a 3-input NAND gate using NAND gates of 2 inputs. Okay, so I'll leave that as an exercise. All right. Now, my question now is there a better way of realizing, of actually constructing a circuit that satisfies this condition? Okay. Now, using this approach, that is where I just write down the expression and then I just write down the equivalent circuit consisting of AND gates and OR gates, or replacing the AND OR schema with the NAND schema. It's not always possible to minimize the number of gates that are required. In this case, we could see that if that we could make use of this row. Okay. Now x and y is 0 in this case, but if we could invert this, if we could somehow invert the output. Okay, so say I just invert the output. Okay, so then the first three rows all go to 0 and the last row goes to a 1. Okay. Now we can realize the truth values in this column um, using this row, okay, which is nothing but the negation of x and negation of y. Alright, but to realize this row, all that we just need is the inversion of this row, okay, which in other words means to say that we need this to be inverted, which is the same as the inversion of the inversion of x or the inversion of y, which is nothing but x or y, which means to say that this part of the truth table can be realized using this expression alone. That is, in other words, we are just saying that this expression is just equal to this expression, which can be easily realized using OR gate as shown here, okay, which can be realized now using NAND gate as follows, or using a set of NAND gates as seen here. So if this is x and y, this would be the inverse of x, inverse of y, and this would be this expression, which is the same as x or y. So we can see that this complex circuit could be replaced with a much more simpler circuit if we could write down the Boolean expression that we were able to compute initially using a simpler expression of this form. Okay. So I hope it has been useful to us, and it may be useful to solve some of the problems in our assignments. Thanks, guys. Thank you. Bye.